Hey everyone, it's Morgan here. So, we're going to be taking a look at the next part of the lecture outline dealing with liquids and solids. And we're actually going to talk about liquids today. So, things to remember about a liquid themselves: one, they flow freely; two, they have a constant volume; and three, it takes the shape of its container. So, liquids, always remember constant volume and take the shape of their container. So I thought this was kind of appropriate, okay, just to take a look at. Actually, I see this scene in my house pretty often. So, properties of liquids that are of interest to us, like surface tension, okay? Here you're going to see some water striders, some bugs that can actually walk on water. Now, it turns out that the surface tension is strong enough that the water striders don't break it because they are so light. And anyone that's ever done a belly flop into a swimming pool understands the concept of surface tension. Now, technically, it's the resistance of a liquid to an increase in surface area. Now, this diagram here really does a good job explaining that. This is the hood of a car, a blue car, and it is freshly washed and waxed and buffed out. And when you have the non-polar wax on the hood of the car and you put the polar water on it, the water has a resistance to an increase in surface area. It doesn't actually want to spread out, so it beads like this. Okay? That's how you can tell you've done a good job washing the car. If there was dirt on the hood of the car, the water would be attracted to the dirt and it would spread out. Okay. Capillary action. You see here two burettes, one that contains mercury and one that contains water. And in the one containing mercury, you see a bit of a dome, something that is concave up, and then on the other side, concave down, okay, what we call a meniscus. Capillary action is the spontaneous rising of a liquid in a narrow tube, like a burette or a straw. Because the glass is polar, the mercury won't be attracted to it because the mercury is nonpolar, just some London dispersion forces. The water, however, is polar, so it is attracted to the glass in the burette and it starts to climb up it. And you've seen this in straws at home. You've seen this using a graduated cylinder at school. Okay, pretty well-known phenomenon. Now, these are caused by cohesive and adhesive forces. Cohesive forces help hold molecules side by side. And what you're looking at here is a penny, and you can put drops of water on the penny. Okay, it works with any coin. And you see this nice dome form. And you can also just overfill a glass of water, and you can see that dome up there at the top of the liquid. Okay, now, in terms of vocabulary, you have to be very careful when using words like together. That could be misinterpreted as a chemical bond. So what's happening is we are holding the molecules side by side. We're talking about IMFs, okay, intermolecular forces, not bonds. Adhesive forces is what will hold the molecules to the walls of the container, okay, which we saw with the meniscus. Probably remember a bit about this from biology. Now, viscosity. Viscosity is a measure of a liquid's resistance to flow. You might refer to it as how thick a liquid is. Glycerol is a really good example. It is the additive that we put in cough syrup to help thicken it up so it adheres to the walls of the esophagus. Okay? Now, glycerol has 3 of these OH groups, which can give rise to an awful lot of hydrogen bonding. And that's what makes the molecules less likely to flow past each other, more likely to be attracted to each other, and that gives it the thickness. You'll notice this in something like molasses or a high-quality maple syrup, maybe even something like a corn syrup. Okay, now we're going to move on into looking into what a solid is. Now, this kind of silly definition was in the freshman chemistry textbook that I learned out of. It's humorous, it's descriptive, but it isn't actually a definition. The state of matter with an arrangement of atoms that are close together, locked in place, and vibrating slowly. I think that's a good definition. And we need to know that solids are going to be characterized by a definite shape and a definite volume. Those are two really important points. So, we're going to categorize solids two ways, what we call the crystalline and the amorphous. Crystalline is a very organized and orderly pattern. Okay? We tend to say that crystalline solids, okay, are arranged well. They are attractive to look at. Very old term, people used to call them true solids. Okay? And you have, in your kitchen, sodium chloride is a crystalline structure. Now, an interesting little point is that the melting point of a crystal tends to be very sharp. It tends to melt at exactly one temperature without strain at all from that. Now, the only problem with this diagram that you're seeing is that it's two-dimensional, and in reality, crystals are going to be three-dimensional. Now, an amorphous solid, there's really quite a lot of disorder in the structure, okay? And the best example really is as if all of the atoms just suddenly froze in time, just wherever they happen to be. I am guessing you are familiar with tar, okay, from maybe doing some roofing or when somebody is redoing the asphalt out in the street. Okay, tar is an amorphous substance. Obsidian, you might have actually been exposed to obsidian. It's what arrowheads used to be made out of. Okay, so these are examples of amorphous substances. Now, the melting points tend to be a little more gradual, not as sharp as with crystalline substances. Okay, polycrystalline. This is what you're really going to encounter. And you'll see this even in something like rock salt or kosher salt, if you have any in the kitchen. Okay? So if we say that a substance is crystalline, it's probably polycrystalline. And there'll be regions of regularly arrayed atoms that are randomly oriented towards each other. And I think that these three diagrams really tie everything together very nicely. Okay, they illustrate what we're getting at really well. Now, let's fill in this table with some examples from your everyday lives. Examples of pure metals: iron, copper, aluminum. I'm not going to put gold in here. That's a different issue. You really, I doubt, have any pure gold. If you have gold jewelry, it's actually an alloy. So, iron, copper, or aluminum, that's made up of atoms. And those atoms are held side by side to each other by something called metallic bonding. We'll return to that in a few minutes because it's really important. Now, an alloy is a mixture of metals, okay? Most gold is actually an alloy. Brass, which is probably the door hardware in your house, is a mixture of copper and zinc. Again, made up of atoms and held side by side with metallic bonding. Now, ionic crystals, any salt that we're talking about will fit this. It can be made up of monoatomic ions or polyatomic ions, doesn't really matter, okay? And what holds them side by side are ionic bonds. Now, you'll notice I'm calling all of these interparticle forces rather than intermolecular, because up to this point, we're really not talking about any molecules. Now, for a molecular solid, it would be made up of molecules, something like carbon dioxide. And these are held side by side only through IMFs. Covalent bonding does not hold molecules next to each other. It'll hold one molecule together. but it doesn't hold molecules next to each other. So we also have the network covalents, and these are fascinating. Everybody likes to use diamond as an example. I tend to like to talk about quartz and stuff like beach sand and glass. These are made up of atoms that are covalently bonded in a giant network, which means they have really high melting points. Okay. And I think we're on to a new page here. So let's look at some properties of crystalline solids, like ionic solids. This is a big old honking piece of halite. This is sodium chloride. This is about the size of a shoebox. It's just not necessarily easy to see that in the picture. Okay? Very high melting point. The ionic bonds that are holding all the particles side by side do an amazing job of attaching to each other. So it takes a lot of energy. You can't melt table salt at home. It takes about 850 degrees Celsius, okay, to melt halite. Although it is water soluble, drop that into water and the whole thing just falls apart, okay? Made up of ions. And everything that we're talking about here is due to Coulombic attractions, okay? So that's back what we're dealing with. Once again, Coulomb's law. Now, molecular solids. Molecular solids are very different. They have lower melting points. They sublime quite easily. Water even has some strange properties, like it being densest at 4 degrees Celsius, which means that lakes actually freeze from the top down. Okay, so you can go ice fishing. Don't understand why, but it's possible. Also, we know that with water, the strong IMFs, when water starts to get cold, will actually cause liquid water, okay, to have a greater density than solid water, okay? Some people like to say this, ice expands, okay? When a volume of water freezes, its volume increases slightly, okay? Which is why you can't put a soda in the freezer. So here's some good examples. The upper left is carbon dioxide. The lower right is phosphorus, P4. Upper right is sulfur, S8. And lower right is iodine crystals. Notice that the dry ice, the carbon dioxide, upper left, and the iodine, lower right, are both subliming, okay? The intermolecular forces holding those molecules side by side are pretty weak. So rather than melting, they actually go straight into the gas phase. You can see that purple cloud coming off the iodine really nicely. Atomic solids, things like a diamond, okay? Each carbon in diamond is bonded via sp3 hybridized orbitals to 4 other carbons. So this is a very big, strong network, okay? Now, when you pull on one, you're pulling on all of them. That's why diamond is so hard, and that's why diamond has such a high melting point. Atomic solids have really high, sometimes called covalent network solids, really high melting points. Okay, metals. A pure metal is a crystalline solid made up of identical atoms. And we need to recognize that metals have very high thermal and electrical conductivity. Remember, the cookware in your house is probably all made out of metal. It is all of the wiring that's in your house, copper, undoubtedly, so good conductor. Now, malleable, meaning we can beat on it and we can shape it, okay, especially the pure metals, not so much the alloys. And ductility, meaning it can be stretched out into wires. Okay, now all of this is because of metallic bonding. So we'll have to talk about that in detail. Now, the high densities of metals are the result of having the atoms being very, very close together, packed in very tightly. Makes it very dense. So this metallic bonding stuff. These are strong but non-directional bonds that hold the metals together. Since they are not pointing in like sp3 hybridized orbitals or something like that, we say they are not directional. Okay. It is often described as the electron C model. Non-directional, so we can shape things. I've used as the example taking a bag of M&Ms, spilling it out on the demo table, and then pushing a piece of duct tape down on top of it. And the duct tape will pick up all the M&Ms, which would be the equivalent of the electrons, and then the duct tape would be all the atoms. And it's quite easily shaped, turned, twisted, folded. Okay? So, metals can be bent, you can stretch them, you can shape them. We've been doing this for 2,000 years. All right, so this is kind of what it might look like, just to have all the positive charges and then all of the negative electrons just floating around on top of them. And these are very mobile electrons, meaning capable of carrying an electric current. Okay, now, if we want to go back to the last couple chapters and think about orbitals and energy levels, if you bring two atoms together, same atom, we're going to say that the atomic orbitals have the same energy level, but we're lying to you a little bit. They're slightly different. Not a lot, but just slightly. So 4 atoms together, you get 4 of them orbitals, and 16. All of a sudden, you're starting to realize these orbitals are getting closer and closer together. By the time you get up to a mole of these atoms, all these orbitals are basically overlapping with each other, which means the electrons can very readily flow through them. This is something that we call band theory, B-A-N-D, band theory. Okay, so even though we say the energy levels are the same, there's slight little differences. Okay, alloys. A substance that contains a mixture of elements that displays metallic property. So I just love the graphics done by this website, Compound Chem. And just undoubtedly every year people end up asking me about gold and the different alloys and difference between white gold, yellow gold. Well, those are just terms that jewelers have made up. Gold is gold, okay? But depending upon what the metals are mixed with, they can take on slightly different appearances, okay? So substitutional alloys are when you take similarly sized atoms and replace each other. This happens a lot with the transition metals. Okay, copper and zinc, similar size. Looks something like this. An interstitial alloy, you have 2 or more atoms of distinctly different sizes. Steel, which is iron and copper, is a good example. And it looks like this. Okay, your network atomic solids. Quartz is an example, okay? 3-dimensional structure like this. We talked about diamond. Diamond has the exact same structure. sp3 hybridized orbitals, all attached to other atoms. High melting point, very strong, wonderful substances. Okay, allotropes. Now, allotropes are different examples of the same element. They're just put together in different forms. We have diamond, which is one of those networks. Then we have graphite. Graphite's fascinating. It's what's in the pencil you're writing with, okay? It is a covalent network 2-dimensionally. And those layers are stacked upon each other, but only held together by London dispersion forces, so they will readily rub off of each other. It would be about the equivalent of putting a deck of cards down, okay, and pushing around the whole deck, holding onto the top card. They kind of spread out, okay? Then the third one here is a buckyball, Buckminster fullerene, C60, 60 atoms in a sphere, okay? These are wonderfully proving themselves to be of help in the medical industry. You can actually use them to encompass medications, and then they can deliver them to different parts of the body inside of these. And then the last thing there is called a nanotube, which are layers, kind of like the graphite layers that are rolled up on each other. Incredibly light and incredibly strong. And if you're familiar with it, the Boeing 787 Dreamliner is built up of these carbon composites. Okay, so that's it for that lecture, okay? We're going to come back and look at some more details about liquids next time. All right, thanks for tuning in. This has been Morgan, signing off.